Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. And in this video, we're going to be looking at Chapter 2, and we'll be looking at how we can use those steam tables to solve problems or find values of properties. As a reminder, the steam tables in our textbook are sorted first in section A1, saturated steam organized by increasing pressure. And we have VL, which means saturated liquid steam, and VV is saturated vapor steam. So these are the volumes, internal energies, enthalpies, and entropies of saturated liquid and vapor steam at that point where they're boiling. These are the two phases that are in equilibrium with each other. This is sorted in A2 by temperature. When you move to the superheated steam table, it's sorted in chunks by pressure, with increasing pressures as you go through the table. And then for each one of those chunks, it's organized by temperature. The first entry in there is the saturated steam temperature. And then we have the specific volume, internal energy, enthalpy, and entropy for each one of those. If no entry is given, it means that it is not a superheated steam at those conditions. If you move on to table A4, it's going to be a similar table for compressed liquids. Now let's try using the tables to solve some problems. So in this first one, we want to know what is the phase of the water at 240 degrees if the measured specific volume is 0.001221 cubic meters per kilogram. So pause the video, pull out a steam table, look up 240 degrees C, and we're always going to start in the saturated table at the given temperature or pressure. So take a moment to do that. Okay, welcome back. So what I found was that the saturated liquid specific volume is 0.001229 cubic meters per kilogram, and for saturated vapor, it's 0.059705 cubic meters per kilogram. Now, how does that help me tell what the phase is? Well, what I need to recall is those diagrams we've had in the previous lessons. In this particular case, we're talking about temperature and volume. So the graph we had that relates to this, T versus V, looked something like this. And in here was the saturated liquid vapor. Over here was my compressed liquid. This is my critical point. And over here is the superheated vapor. So what this is telling me, the numbers from the table are telling me the point here and here for a particular temperature, in this case 240 degrees C. And my number is smaller than this, so my value is somewhere over in this region. Therefore, what I have is a compressed liquid, because the volume is less than the volume of the saturated liquid. So a similar problem. Now I want to know the phase of the water at 240 degrees C when the measured specific volume is 0.063521. Now, we just looked up all of this information. In this case, again, the values are on the curve, the TV diagram. So 0.063521 is greater than the volume of the saturated vapor. So therefore, my point is somewhere over here, making this a superheated vapor. And now you're probably starting to see why I abbreviate these all the time, so I would abbreviate this as SH. So one more problem, 240 degrees C, specific volume is 0.03875 cubic meters per kilogram. Now by now you've probably guessed we're using the same data points and the same information. In this case, our specific volume is between the value for the saturated liquid and saturated vapor, and so therefore I have a saturated mixture. I abbreviate this with just SAT. Okay. But that sort of is an unsatisfying answer, right? It says it's somewhere in this region. Maybe we would like to know how much is liquid and how much is vapor. We use quality as a way of defining this. In our textbook, quality is a lowercase q, and it's the fraction of mass in a vapor-liquid system that is in the vapor phase. Very important that it's in the vapor phase. So if you do this for any particular instance or property, if Q is vapor, 1 minus Q is therefore liquid, right? And if I do this for any property, and they use M to designate a property, now M might represent the volume, or the specific volume, or the enthalpy, or the internal energy, or the entropy, any number of these variables. But they're going to, for one of our properties that is in the table, I could use any of these with the same definition, all right? And so this is great. It just says the amount that's in the liquid phase times the property value of the saturated liquid plus the amount that's in the vapor phase times the amount of that quantity for the saturated vapor. If you solve this algebraically for Q, we end up with Q is equal to M minus ML over MV minus ML. I prefer to write this, let's write it out, for instance, with the volumes. In that case, I have the specific volume that's the actual value minus the saturated liquid specific volume over the difference between the saturated vapor and saturated liquid volume. If we were to apply that to this particular problem using the numbers from the previous screen, we have 0.03875 minus 0.001229 meters cubed per kilogram, all over 0.059705 minus 0.001229 meters cubed per kilogram. Meters cubed per kilogram over meters cubed per kilogram cancels out. And so I'm left with 0.6416. Okay, so what does that mean? It means this mixture is 64.2% vapor, and the balance, or in this case 35.8%, is liquid. This concludes this video lesson. In our next lesson, we're going to look at stretching our skills using these data tables. Thank you very much for your time.